So we're going to take a look at continuity here in two parts, and in the first part we're just going to introduce you to the idea. So the simple way to think about continuity is being able to move your finger along the graph without having to pick it up. So basically we could say here that you could trace the graph with your finger and not have to lift it. So let's take a look at some graphs to see what I'm talking about. In this first one, if you take a look on your calculator at this graph, we can also do it algebraically. So it's not a bad idea to get a little bit of practice. If this was a function, absolute value of x minus 2 over x minus 2, it's a piecewise graph. For the absolute value function, the problem is going to happen at x equals 2. So for everything less than 2, I have negative of x minus 2, and the bottom is still what the bottom was. And for when x is greater than or equal to 2, no change is needed. So if I take a look at my pieces now, I can simplify this down. That's just going to be negative 1. The two x minus 2's disappear. And then the other one is just going to be 1 as the x minus 2's disappear. So this is what my function looks like. It looks pretty complicated when you first see it, but if we change it into a piecewise graph, it actually just looks like this. And according to the way I've got the equal sign here, it would belong to this point and it would not touch that point. So if you imagine trying to move your finger along this graph, everything's okay until you hit here, and then you have to move your finger to get up to here, and then everything's okay. So we wouldn't consider this a continuous graph. So this graph is discontinuous at x equals to 2. Now, if you think about the way you move your finger, we call this a jump discontinuity. And usually when you have a jump discontinuity, it's because a piecewise graph does not fit together. We'll take a look at some other ways that a function can be discontinuous, but this also just helps us visualize what we're doing. So running my finger along, I can't do it, I have to pick it up. And what I do is I jump, so we call it a jump discontinuity. Okay. So, well, it's hard to see in here, so maybe I'll just annotate it for a second here. This, for example, should have said, let's say 2 to the right and 2 to the left. Might be hard to see there, so I'm not sure if that's the same as your notes, but you can adjust them accordingly. So for some reason when I print these, it doesn't always render exactly. So this means the limit as x approaches from the right side and if we look up in our picture here, as I approach from the right side, that would be this. The value I hit is here. So as I approach, that limit equals 1. The other one is the limit as x approaches from the left side. So as I approach from the left side here, when I get very, very close, I'm looking at a value of negative 1. So one of the ways we can recognize a jump discontinuity is when we look at the two limits, they are not equal. Generally, if the left side and the right side limit don't line up, that graph is not continuous. So that's one of the things that we'll learn to recognize without having to use the graph, is that if the left side limit and the right side limit don't touch, then it can't be a continuous graph. And that also brings us to condition number 1 for continuity. So maybe I'll put it right here. The limit as x goes to a of f of x must exist. If it doesn't exist, then there's no point in looking anymore. And how do we know that it exists? If you remember from previously, that means as x goes to a from the right side, you get the same limit as x goes to a from the left side. So if you approach from both sides, you get the same limit. The final thing that we need to make sure of is that when that limit exists, that it's the same as the function. So when I evaluate the function, we could summarize all of that by saying the limit as x goes to a of f of x is the same as the value of the function. So this is what continuity means in terms of limits. Okay, so we're going to take a look, because limits are still new to us, we'll practice this. So let's take a look at the continuity at f of 1. So the first one asks for the limit as we approach from the left side, so that's going this way. So as I approach from the left side, the value is 1. As I approach from the right side, the value is 0. And as I approach from both sides, that limit for 1 does not exist because they're not the same. So immediately I know this graph is not continuous, and you can see it in the picture here because there's a jump. If I actually was to look at this picture though, f of 1 exists. According to that dot right there, f of 1 is 0. So this is what you'll have to get used to, and mostly it's new to you because continuity and limits are new. So interpreting the limit is probably the hardest part of this for most of you. So I'm going to erase my diagram here, and we'll start fresh. Let's look at as we approach 0. So as I approach 0 from the left-hand side, this is where I'm coming down from, and I hit very close to 0. And as I approach from the other side, that's okay too. I also get to 0. So I could say that the limit for x approaching 0 is 0. So this is possibly a continuous graph just looking at those limits. But now when I take a look and consider what the function is, there's a hole here. If I ask the function, that is the value of f of 0, which is 1. So the function does not line up to the limits, so this is not continuous either. So we consider a function continuous. This is the 3 things that I do. I take the left-hand limit, and I take the right-hand limit, they must be the same. That way I know that the limit as x goes to a of f of x exists. If I can't get that, I'm already finished. I know it's not continuous. So the limit exists, and then I also have to check the value of the function at a. It must equal the limit in order for it to be continuous. So if you think about what these 3 things mean, this is moving your finger across the graph from the left-hand side and the right-hand side. And remember, limits to exist don't actually have to evaluate at the point itself, just as close, arbitrarily close as we want to be. That's why we actually have to check the value in addition to the limit, because the limit might exist when the function does not. Or they might have a different value like they did over here. So we consider a function to be continuous on an open interval if it's continuous everywhere in the middle. So we'd say if the limit as x goes to, let's pick another letter here, z of f of x is equal to f of z for all z in a b. Those of you that are nerds like me will like to write it like this. But basically that just means any point I pick in there has this property that we just discussed. In addition, if we want to do it in a closed interval, we have to make sure it exists at the endpoints. So all we're doing now is just making sure that it's continuous everywhere in the middle. And as I approach these, sorry, that should be a B, it also lines up to the endpoints. And of course, when we're working with a closed interval, we don't actually approach from the left side. I only have to approach A from the right because I don't have anything after it. And similarly, I only approach B from the left. So let's take a look at another example here. We'll discuss its continuity. So in this graph here, it's a piecewise of a whole jumble of things. And we're going to take a look at f of x equals 1 first. So if we want to evaluate the function, there's where the function equals 1, right where the dot is. So it says that point is 1, 1, so I know the value is 1. So it's kind of crooked there. Now let's take a look at the limit as we approach from the right-hand side. So as I move from the right-hand side, this gets very close to 2. As I approach from the left-hand side, this also gets very close to 2. So we can say no, it's not continuous because the limit does not equal the function. I'll try again for -1. Let me just clear my working area here. So for -1, as the function is right there with a value of 0. Now as I approach from the left, that's this way, it's going to approach, let's see here, 0. And this function is not defined for that side of the graph, so we don't need to look at it. Remember, if you actually check into it here, the interval you're looking at is from -1 to 3, but not including 3. So we would only need to get continuity from this part of the graph, the left side, because it's not defined on the right. So is it continuous? Yes, it is. And you can see that if you were to use the simple definition, you can put your finger on it and move it all the way along, and it would be continuous there. Now, the intervals that it's continuous, if we look at it, you can do this by thinking about where you have to start moving your finger. So here it's continuous until I hit there, not continuous at 0. It's continuous all the way through here, but then it jumps down to that spot, so it's not continuous. Continuous until I get there, then it does not exist, so I have to move my finger, pick it up off the graph, and finally, not continuous there. So if I were to write these down as intervals, that's from -1, which I can include, but not including 0. Then it would be from 0 to 1, not including it. Then from 1 to 2, and from 2 to 3. So the next question is asking how can we fix the continuity. So again, I'll just clear my old graph off. So the first one is how can we make it continuous at x equals 2? So this is the region I'm looking at. What I'd want to do is fill that hole in. And I'd want to make f of 2 equal to 0, and then I'd have this picture where I could move right through it without picking my finger up. And changing f of 1 would remove the discontinuity. So here's f of 1 right here. And what I have to do is I'd have to put that dot right back up there. So it's, I don't know why it's crooked here. I got this from your textbook, but anyways, that's supposed to be the value 2. You can see in the diagram here. So if we had f of 1 equal to 2, that would fill in the hole so I could move through the point without picking up my finger. Okay, is it possible to remove the discontinuity at x equals 0? So this is the region we're thinking about. And in this case, it's not removable. The problem is we jump over an entire region of the graph. It's possible to fix the graph, but the only way we can do that is to change the piecewise definition. And the easiest way to do that would be to move the graph there like this by translating it higher. But it's not as simple just filling in a hole like we did for these ones. Okay, so usually when we refer to discontinuities, we call these ones here removable. Because we just have to change one of the values in the function. This, on the other hand, is a jump discontinuity. We don't generally consider those as being a removable discontinuity. Okay, so now we're going to move on here and take a look at the limit as x goes to 5. So again, in this situation, we'd have a piecewise graph where it said this is negative x minus 5 over x minus 5 when x is less than 5. And it's just, x minus 5 over x minus 5 when x is greater than or equal to 5. So the piecewise definition is negative 1 when it's less than 5, and 1 when x is greater than or equal to 5. I'll just make that a little neater. So this is like approaching from the left side, and this is approaching from the right. So this limit does not exist because there's a jump. Now it's hard to see in your picture, but the again, I don't know why it renders it wrong, but it's actually looking at the limit from the right side. So if we were just looking at it from the limit from the right side, this is going to be 1. And if we look over here and we want to evaluate the limit as 3 goes from the right side here, then if we try to evaluate it, what you can think about, there's going to be a division by 0 at 3 here. So if we were to think about the graph, there's going to be an asymptote. But we don't know which way that asymptote is going to go. Is it going to be going up like this towards infinity, or down like this towards negative infinity? The way to figure that out is on top, if I was to evaluate it from the left, I would have, excuse me, I would have root 3 minus 4, which is a negative value. And on the bottom, when I evaluate a little more than 3 and take 3 away, this one's positive. So that tells me a negative divided by a positive is going to be negative infinity. And similarly over here, this is going to be a little more than 5 plus 2. That's a positive number. And it's going to be dividing by 0, so I'm going to expect an asymptote in my answer. But a little more than 5, take away 5 is also positive. So we'll end up with an asymptote that goes towards positive infinity. Now when you're going to reason about continuity, there are a family of graphs that basically all the ones that you know of, things like polynomials, that are continuous everywhere. Polynomials, sine, cosine, log, what else do we have there? Tangent. Now remember, these ones have some problems, but the key thing is, as long as they're defined, these functions are continuous. So if you wanted to talk about the continuity of a graph or think about the continuity, sometimes you can use the fact that these ones that we know are continuous just by knowing that the families of graphs in them are continuous. So we'll try that. Just take a look down here. Let's see here. So the first one, actually maybe before we try one down here, we'll just go over how the limit laws extend to continuity. So first of all, if you have the sum, difference, product, of two continuous functions, then the new function is also continuous. Composition of continuous functions are also continuous. Now, if you have this situation where you divide two functions, it's continuous as long as g of x does not equal 0. That's the only concern when you're dividing. So for example, this polynomial here, this is the difference of x squared and 2x, two continuous functions, and then subtracting 5. So, we're not going to go through that lengthy explanation there, but basically you can prove that that polynomial is continuous because each piece of it is continuous. But if we did this here, we wanted to show the following ones are continuous. X squared minus 2x minus 5 is a polynomial and therefore continuous everywhere. And the square root graph is going to be continuous anywhere that we don't end up with a negative. So this would be, this graph here is continuous provided that x squared minus 2x minus 5 is greater than or equal to 0, because the square root graph is a continuous function, and this graph x squared minus 2x minus 5 is continuous. Taking their composition makes a new continuous function. The only rule, though, is that this must be greater than or equal to 0 for it to exist. Again, if we look at the pieces over here, this is a continuous function, x squared minus 2. This is a continuous function, and the absolute value is also continuous. So their composition is going to be continuous, but the only thing I have to be careful of is this division by 0. So the new graph that comes out of this is continuous everywhere as long as x squared minus 2 does not equal 0. And we can quickly figure out that x cannot be plus or minus root 2. So this new function is continuous everywhere as long as this domain is upheld.